Welcome to a video tutorial on solving for the rate law using the method of initial rates. Before we get to some actual data, let's look at a simplified example here with some nice whole numbers and understand the method we're going to do. Here we have some reaction with just one reactant, and the rate law in its general form would be the rate is equal to some constant multiplied by the concentration of A raised to some power of X. To solve for the rate law, we need to determine the value of x, or the value of the exponent, and then we need to determine the value of the constant. The exponent tells us the impact that changing the concentration has on the rate. So we want to compare the change in concentration to the change in rate, and we are going to do that by doing a ratio of the two trials. So trial 2 divided by trial 1. On the left-hand side here, I've rewritten the rate law and just indicating which trial we're going to look at. So the rate from trial 2 is equal to some constant K multiplied by the concentration of A in trial 2 raised to some exponent X. And the rate in trial 1 is equal to the same constant K multiplied by the concentration of A in trial 1 raised to that same exponent X. To solve for our exponent, we are going to set up a ratio and compare the left side to the right side. So we're dividing trial 2 by trial 1. Let's substitute in our numbers now. Now I'm going to simplify the left side and the right side, still keeping them separate. The left side simplifies to 8, 80 divided by 10. The right side we need to do a bit more work on. The first thing we can see is that since the constant is the same, we can cancel those out. And then we can use our exponent laws to recognize that 4 to the x divided by 2 to the x is the same as 4 over 2, all raised to the power of x. Or what we have is 8 is equal to 2 to the power of x. Mathematically, now what we're doing is simply solving for the exponent, and you might be able to see through inspection by just looking at it that our value for x is going to need to be 3. 2 to the 3 is equal to 8. However, we want to think about this equation in terms of what it means for the concentration and rate. So what's this saying? What does the 2 represent? That represents the increase in concentration, or the concentration increased by a factor of 2. The left side of the equation, the 8, is how the rate changed in response. So this simplified equation tells us that when we increase the concentration by a factor of 2, the rate increases by a factor of 8. And if we cube the concentration, that gives us that rate increase. Now that we've solved for the exponent, we can solve for the value of our constant K. Since we have experimental data, we can solve for K by taking our values from one of the trials and substituting them in for those two variables. So let's do that now with trial 2. Okay, so when we solve for K, we get a K value of 1.25. Now we have the solved rate law for this reaction. The rate is equal to 1.25 multiplied by the concentration of A cubed. Once we've solved for this rate law, we could now use this law to predict the rate at any concentration. Let's now take a look at an example problem with some real concentration time data. Let's now look at an example with some real data. In this reaction here, we have our rate law equation that relates the change in concentrations to the rate, and we have our unknown exponents, and that's what we're trying to solve for, the exponent on NO and the exponent on H2. In our simplified example, we only had one reactant. So what we need to do first here is be able to isolate one reactant. Let's look at this table. We can see that between trials 1 and 2, there's no change in the concentration of NO. But the concentration of H2 goes from 0.1 moles per liter to 0.2 moles per liter. Since the concentration of NO doesn't change between trials 1 and 2, any change in the rate will be entirely due to changes in H2. So let's start off by looking at a ratio of trials 2 to 1, only focusing on the concentration of H2. The first thing we're going to do is look at what factor the concentration of H2 changed by. So I'm going to do trial 2 divided by trial 1 for the concentration of H2. So we can see that trial 2 to trial 1, we have doubled the concentration of H2. Now let's look at how the rate changed in response. Once again, I've done a ratio of the rate in trial 2 divided by the rate in trial 1. And we see that the rate also doubled. Since the concentration of NO did not change, that means that the rate is entirely dependent on the change in concentration of H2 raised to some exponent y. Whereas we saw, when the concentration of H2 doubles, the rate doubles as well. And so by inspection, we can see that our exponent for H2 is equal to 1. It's first order with response to H2. Now let's move on to the NO reactant. For this reaction here, we need to select two trials where the concentration of NO changes, but the concentration of H2 stays the same. So this will be trials 2 and 3. Using what we did here for H2, can you pause the video and try to find the exponent on NO using the same method by doing a ratio of concentrations, a ratio of rates, and then solving for the exponent. So pause the video now, try this, and then we'll see what you get. So when the concentration doubles of NO, the rate increases by a factor of 4. So the rate is equal to the concentration raised to some power x. And once again, we can see by inspection that our exponent is equal to 2. So my exponents in my rate law equation are NO raised to the power of 2 and H2 raised to the power of 1. Let's now solve for K. To solve for K, we are going to take the data from one of our trials, and we'll choose trial 1, and substitute the values in and solve for unknown. I'll rearrange the equation first to solve for K, and then substitute in our data. So here's our constant, 6.875 times 10 to the negative 4. You can solve for the units on K as well at the same time. However, I'd like to do them separately. So I'll write the same equation as I have up here, and rather than substituting in the values, I'll substitute in the units. And now we'll simplify. So the units on K are liters squared, moles to the negative 2, seconds to the negative 1. Here is our solved rate law equation, where I have my constant with units, and then I have my solved exponents, 2 and the 1.